हेलो, मेरा आवाज आ रहा है? Am I audible?
Yes, sir.
Now you are also audible. Yes. Okay.
Okay, fine. So, good afternoon, all. Welcome to the second session of fourth day of FDP on robotics. As it is said by Dr. P.S. Jagdish Kumar, when human is full of emotions, robots are full of success. We can imagine the power of robotics. I welcome today's speaker, Dr. Prasid Trivedi, sir. Sir holds PhD from Systems and Control Engineering, IIT Bombay, and MTech from Department of Electrical Engineering, IIT BHU. Currently, he is working as an associate professor in the Department of Electronics Engineering at D.Y. Patil University, Navi Mumbai. His current research interests include fractional order system, sliding motor control, and event-triggered sampling. His topic is robotic manipulator design using MATLAB. He has several papers in refereed journals and international conferences in various areas like nonlinear control, sliding mode control, finite time conversions. So I welcome you, sir, and I request you to start the session.
Thank you, Sushma madam. We have had a very fruitful 3.5 days sessions ranging from robotic operating systems to non-holonomic motion planning, and very advanced and research-oriented talks been given in this session. These two sessions will be very basic sessions. They are planned to balance out the advanced.
हाँ, मैंने आपको इसलिए बुलाया है कि इसके शिंदे सर पता है क्या आपको? He is BOS member of engineering.
Vishwas, sir?
Yes, ma'am. Sorry.
Yeah, I will make it. Okay. Yeah. Okay. So this session is planned as a very basic session. We'll start from just a single rigid body. Then we'll introduce the concept of rotational metrics. We'll introduce kinematics, forward kinematics, inverse kinematics, Jacobian, and workspace of robotic manipulators, and also some dynamics, along with some programs in MATLAB, and how MATLAB can help in designing this robotic manipulator. So, in this FDP so far, all talks have been concerned with the mobile robots. Now, mobile robots is a very recent research area. Uh, 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 the research has been going on since many years, but the technology has picked up, which does those theoretical research nowadays. And mobile robots, mean the robots which can move around in certain area and do certain design tasks. So, but the robotic manipulators have been uh, older than mobile robots, and they have been used in industries and automation since many years, almost 40, 50 years. So they have been used. And the design of robotic manipulator was one of the earliest and richest research area in robotics, in the field of robotics. Okay. So we'll start by introducing the single single link manipulator, which is just one single rigid body. Now, let me draw a two-dimensional plane. We are going to restrict ourselves to planar manipulators, that is, the manipulators which are only in two-dimensional space. Yes. This planar single manipulator can be seen like this. There is a joint at origin. This joint we will call as, using the terminal robotic literature, we will call this as a revolute joint. A revolute joint meaning the robot can move around this joint. So this joint can revolve. Right? So this single link can revolve around this joint, and this body is rigid. Right? So this is a rigid body, not flexible. We have flexible link manipulators also with their own application. We are going to concern ourselves with only rigid body. Rigid body means when the force, external force or torque are acted upon the body does not deform, body does not change its structure. Right. So if after application of the force, this link deforms like this. Right? So if I apply a force somewhere here, right, and if the body deforms like this, then this is not a rigid body; it is a flexible body, and they have their own applications. And uh, along with the complexity in analysis and design, uh, we are going to talk about rigid body. So this is a rigid link, rigid body, and at the end of this body we have something called a gripper. Yeah? And the job of this manipulator is to manipulate objects in this two-dimensional plane. This manipulator can pick some object and it can put it on some other place uh, in this two-dimensional plane. But now, as the simplicity of this manipulator suggests, it cannot cover the entire two-dimensional plane. Correct? Only the location that can be covered by this manipulator is this circle. It can cover only the locations on this circle. It can pick the object on this circle, and it can drop the object on this circle as well. Right. Uh, then, if we want to describe how this the movement, the motion of this manipulator, then we need to describe the location, the position of this joint, and this joint is also called. Uh, I said it is a gripper, but in the robotics uh, literature, it will be called as end effector. Is an end effector. So this end effector's position is required to be analyzed. Where this end effector is moving when we apply some torque to this manipulator via a motor connected at this location, uh, at the revolute joint. we can revolve this manipulator, and when we revolve this manipulator, we want to study its motion, and we want to study the motion uh, without first we want to study the motion without concerning about uh, the force that is acting on this manipulator, right? So we'll just study the position and the velocity of this end effector. Now, in the standard notation x and y axis, this position will be well known to everyone. This position of end effector will be L cos theta, and y position will be sin theta. Okay? Where L is the length of this manipulator. Right. So now what we have done here is we have assumed that we know the theta, we know the angle by which the manipulator has rotated with respect to the horizontal x-axis, positive x-axis, and then from that theta we have derived the position of this end effector, position of this manipulator in Cartesian coordinate x and y. That so this problem of computing the position from given angle is called the kinematics problem. And when we move to two-link manipulator, we will see suddenly the complexity has increased. Right now, it seems very simple. So when we consider this end effector as a point in this two-dimensional space, and the position vector of this end effector is it can be denoted as xy, which is the position vector, and we have computed position vector using the knowledge of theta, using the knowledge of angle. Okay. Now, the related problem that you might come across in the literature of robotics is called inverse kinematics. This problem is considerably harder than kinematics problem. Inverse kinematics problem requires us to find the angle given the position. So if we are given the position of the end effector, then we have to find out the angle. So for this single link manipulator, it is very easy to know. Everyone knows theta is equal to tan inverse x y by x. This is inverse kinematics of this single link manipulator. Okay, so we have kinematics, we have inverse kinematics. Kinematics uh, uh, requires us to know the angle, and then from the angle we will compute the position in Cartesian coordinates. And in inverse kinematics, the position in the space is given in Cartesian coordinates, and we are required to find the angle of uh, uh, of the manipulators joints. Okay. So now, now if we rotate this manipulator further, let's say we have rotated it further at this location, and we would like to know the position at this location. Position here. Now let me call this first angle theta 1, and now I have rotated. So I know the manipulator is at angle theta 1. Uh, Maybe I know, maybe I don't know. Let us rotate this manipulator from theta 1. We will increase the rotation and delete this L, and will show that I am rotating this manipulator by additional theta 2. After theta 1, I have rotated it additionally to theta 2, and let me call it this coordinates as x1 and y1, and this new coordinate. Here, this new coordinates as x2 and y2. Now, what is x2 and y2? Well, let us write the expression for x2, that is equal to L cos theta 1 plus theta 2, and y2 is equal to L sin theta 1 plus theta. Now, using those trigonometric formulas, we can easily write them as L cos theta 1 okay. Now we observe that L cos theta 1 and L sin theta 1 are the previous positions x1 and y1. Here also L sin theta 1 and L cos theta 1 are the previous xy coordinates. So I can write this new position in terms of previous position. I can write this x2 and y2 in matrix form is equal to some matrix here, and which is multiplied by x1 y1 previous position. So what will be that matrix? That will be cos theta 2 minus sin theta 2. So now we see that we don't need to know the previous angle theta 1 if we know the previous position. So if we know x1 and y1, if we know the location of the end effector, uh, and then we rotate the manipulator, the end effector by theta 2, then we can find out the new position x2 and y2 of the end effector only using the knowledge of theta 2 only. Right? So this is a matrix which is in terms of only theta 2, and this is the previous position vector, and this is the new position vector. Right? So now these matrices are called the rotation matrices. Even they carry a lot of importance in kinematics of manipulators and the kinematics of robotics. They form a uh, special set called a group in mathematical theory, and groups carry very nice properties, and you can analyze very complex manipulator if we use these rotation matrices in describing the kinematics of the robot. Right? So now when you study further research oriented robotic manipulation, then you will always see the kinematics being described in terms of rotation method. Okay. Now, now that we have introduced kinematics, inverse kinematics, and rotation matrix, then we will introduce a new term which is called workspace. I have already mentioned about this term called workspace. What is the workspace of this manipulator? So workspace of this manipulator is just this circle. It can move only around this circle. So if you have some application which requires this manipulation of objects on this periphery of this circle, then this kind of manipulator uh, is adequate and it will serve the purpose. But now, if you want to manipulate objects in the plane, entire plane, let's say there is an object here, and you want to manipulate this object from this location to this location. Now, can this manipulator do this job? It cannot do this job, obviously, because this manipulator will not be able to reach these 2 points. So now we have to improve something called the geometry of uh, this robot. These are also called geometries of the robot. So we have to improve the geometry. So how do we improve the geometry to make such that this manipulator can cover this two-dimensional space? Entire two-dimensional space is not possible because it is infinite, but at least it can cover something more than this just circle. So one way is to add something called a prismatic joint. What is a prismatic joint? That was a revolute joint, and prismatic joint can give you translational motion. So this is, let's say, your manipulator with revolute joint. Here you have a revolute joint, and then you can add here at the end effector, you can add a prismatic joint, which can give you movement. And at the end of prismatic joint, we have the end effector. Okay, so this is one way to achieve uh, the workspace that is something more than just a small circle. So for this uh, end effector, what kind of workspace can we imagine? This maximum length, you can consider this maximum length up to, let's say, here. So it can take care of all the objects in this region, and the minimum length probably here. So it can take care of all the objects in this annular region. So we call this kind of region annular region. So in this annular region, this manipulator can manipulate the object. And here this joint is prismatic. To achieve manipulation in this two-dimensional space is to add second revolute joint instead of a prismatic joint, and that is our entire session will be about those kind of manipulators, which is popularly called two-link manipulator. So if you search literature on two-link manipulators, you will find this kind of manipulator. There is one revolute joint here. There is another revolute joint. So and now both the links have their angles theta 1 and theta 2. Okay. So now and the length of both the links are okay. Now again we want to perform similar analysis as we did for the single link manipulator. What kind of analysis we want to perform? We want to find the kinematic equation. What is the kinematic? That is given theta 1 and theta 2. Given theta 1 and theta 2, compute x and y position of end effector. Then the problem of inverse kinematics. Given xy position, compute theta 1 and theta 2 both. Right? And then we also want to find out workspace. what will be the workspace of this manipulator, in which region this manipulator can manipulate the object. So these three properties or characteristics that we saw for the single link manipulator, the same properties or characteristics we want to find out for this two link manipulator. And now, if we think about it, this has become immediately become uh, much more complex problem than the previous one, than the single link manipulator. Just kinematics is uh, 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 quite difficult. Not only inverse kinematics. Inverse kinematics uh, most of the times have singularities. We'll see what singularities are. So inverse kinematics is much harder, and even the forward kinematics is uh, hard for this. I will not derive uh, the equations. I will just write the kinematics equation here right now, and we will use the shortened notation. The shortened notation we'll always find in robotics literature because of appearance of this uh, term cos theta 1, sin theta 1, and we'll come across terms like cos theta 1 plus theta 2, like this. So there is a shortened notation used for cos theta 1, which is called T1. For sin theta 1, the shortened notation is called x1. So for cos theta 1 plus theta 2, the shortened notation is T12. So in this uh, in this terminology, so we can write the forward kinematics of this two link manipulator as the position x of end effector will be L1 E1 plus L2 E12, and y is equal to L1 S1 plus L2 S12. Okay, so this is cos theta 1 plus theta 2, sin theta 1 plus theta 2, cos theta 1 and sin theta 1. Okay. So now if we are given both the angles theta 1 and theta 2, we can find out the position of end effector easily. But now inverse kinematic problem is extremely difficult. I'll also, I think I have some images also. Yeah. So this is the use of this tooling manipulator. This I think I planned to draw on this image, but then I drew my own image. No problem. So now, yeah. So second image that I want to put here is about the inverse kinematics, and it shows the. Now you can see that the problem of inverse kinematics, the solution may not exist. Why it is difficult? Because it the solution of inverse kinematic problem, that is given xy, right? So this xy location is given, and you need to find out this theta 1 and theta 2, for which will put that end effector at given location. Right? So if you want to find out these two angles, so this inverse kinematic problem solution may not exist. Right? It is obvious because if the workspace, if this xy point is outside of the workspace, then you are not going to find any theta 1 or theta 2. Or the solution may be multiple solutions. Right? As you can see in this figure, for this same xy location, we have two solutions. You can have end effectors like this also, or you can have end effectors like this. So you have two solutions for the same xy, and which solution to select is another interesting issue. Is how to optimize, and based on the current location, let's say you can say if the ini- initial uh, initial location of initial location of the manipulator was like this, then then this configuration should be reached. This configuration should be reached if the initial configuration was like this, then this configuration can be reached. But how does a program or control or know which configuration was there, and from that which inverse kinematic solution is to be adapted? Right? Those are very difficult problems. Okay. So for this tooling manipulator, we have seen uh, kinematics, we have seen inverse kinematics, and then okay, we have not yet seen inverse kinematics, but inverse kinematics is very complex. I will just give you one equation for theta 2, which uh, gives us plus or minus, because you see here there are two solutions for each xy. So you have two values two values of angle for each given position. So for this tooling manipulator, you can try to derive this inverse kinematic equation for this exercise for beginning, to get the feel of how this manipulator kinematics work. Uh, but it will be hard. It is hard to derive this inverse kinematic equation. Now, so now we have seen kinematics, inverse kinematics, and now we want to look at the workspace. Now here also it is quite evident that the workspace will be annular region, with larger annular region than the prismatic joint. The prismatic, for the prismatic joint, if this joint was, instead of revolute joint, if this was prismatic joint, then the annular region was ending at this, right? Angular region was ending here. But for this revolute joint, the annular region can extend inside, right? So the annular region is expected to be something like this. This is the kind of annular region that is expected. Now we can plot this annular region in MATLAB, the workspace in MATLAB, and that is the first analysis we are going to do in MATLAB. So let me open up my MATLAB. Are the fonts visible, or do I need to increase a little bit? Maybe increase. Okay, I think these fonts are sufficient. Right. So let us start with the link 1 length. Link 1 length. Let us keep it 0.4 meter, and link 2 length will keep 0.3 meters. The theta variation is from 0 to 2 pi in the steps of, let us keep the steps of 0.1. Right. So how are we planning to uh, plot the workspace? We will fix some value of theta 1, sorry, theta 2, and then we will revolve theta 1 from 0 to 2 pi. Then we'll take theta 2 into the next step, and again revolve theta 1 from 0 to 2 pi. That is the kind of approach that we will take to plot this workspace. So both the angles we are going to revolve from 0 to 2 pi. So we have taken theta array as 0 to 2 pi, and then we will have the same. Then we will have the for loop. So the for loop will be something like this. 1 to the count for the for loop will be equal to length of theta, right? I will be used for uh, theta 2, counting theta 2, and j will be used for theta 1. Right? Up here. Right? So j is for theta 1, and we will now compute the x and y position. Xij is equal to L1 from our kinematics equation. L1. So let us have a look at the kinematic equation of this. L1 cos theta 1, L2 cos theta 1 plus theta 2. This is our kinematic equation for L1 into cos. Now for theta 1, we will have I. Here I counting for theta 1 and j counting for theta 2. L2 cos theta 1 plus theta 2. And the y coordinate from the kinematic equation will be L1 into sin theta 1 plus L2. Okay, so then we have computed the x and y position from using the forward kinematic equation, and then we want to plot these points. So to plot these points, we will have to use third variable, and we will use the surf command. For that, uh, we will have the third variable as all one, and then we can use the surf command x y z, or x y z should give us the workspace of this tooling manipulator. Okay, so save. Yeah. Now we, if you can see this workspace of tooling manipulator, this is Z. Actually, this is on the uh, plane, XY plane only, but since we wanted to see this annular region properly, we have kept Z equal to 1 so that we can see this properly. We can make it 0 so that we, if we want to see this workspace on the plane itself. Right? So we can see that the workspace of this tooling manipulator is this angular region. Here you have the origin, your base link starts at the origin 0, 0, and then your both the links can cover this entire region in this 2D plane. Okay, so this is the workspace for your two-link manipulator. Okay, so this manipulator and effector can move to all the points in this region. So that is a very important analysis to be performed when designing an industrial robot or any manipulator mechanism. That what is the workspace of your mechanism? If someone has used 3D printers. So then 3D printers come with their workspace area, right? So they mentioned that the workspace of this 3D printer um, uh, end effector is 15 by 15 by 15. Like that. So that workspace area is very important to be analyzed first when we have some robotic manipulators to be used for application to be deployed for some application. Okay. So yeah. So then um, with this kinematics, inverse kinematics, and workspace notions, there is a related notion of Jacobian. And how does Jacobian come into picture? Because the kinematics is the study, by definition, kinematics is the study of position and velocity of the rigid body without worrying about the forces. Right? In kinematics, we study position and velocity, both, not forces. But right now we have studied in this kinematic, forward kinematics and inverse kinematics, we have studied only position. Right? So theta 1, theta 2 are the position of the link, both the links manipulator, and x and y is the coordinate of the end effector. That is your um, that is position of your end effector. Okay. So now what about velocity? To find out the velocities, we have to differentiate these equations. So we have to differentiate these equations with respect to time to find out the velocity. Okay. So again, I am not going to derive the velocities. I will just give you the equation for the velocity. X dot is equal to minus 1 x1 theta 1 dot minus 2 x1 theta 1 dot y dot is equal to x1 t1 theta 1 dot plus. So these are this is the way velocities are related. So now we can not only talk about position of the end effector, but the velocity also. Now, if we are given the velocity of theta 1 and theta 2, right, so that let's say theta 1 is varying at 2 degrees per second. Right? So if we have used some motors for this manipulating this revolute joint, right? So you may have stepper motor or servo motor, and the servo motor is rotating at the rate of let's say 1 degrees per second. Uh, so both the angles are varying at 2 degrees per second. Then at what rate the end effector is moving. Right? So that is also an important information to know about this manipulator, because you want to take an object from one location to another location in the workspace, right? In the workspace, we want to take the object from one location to another location, but we also want that object to reach its destination in a given time, in some given time. It should not happen that we start the movement and after an hour the object is reaching its destination from the source. Right? So that is why the velocity, knowledge of velocity is important, and we may want some desired velocity there. We may want the object to reach from the source to the destination location in given time, in some time frame. Right? So for that, we need to set the velocity. We need to know the velocity of the end effector, and this equation gives us the velocity of end effector from the velocity of theta, from the velocity of angles. And why this is important? Because velocity of angles are some variables which we are manipulating. We are putting actuators at these revolute joints, and we are rotating the motors at certain velocities, and from those velocities we can derive the velocity of end effect. Okay, so now uh, some of the participants may have already seen these equations and may have already recognized that these are these equations can be put in the matrix form like this: x dot and y dot is equal to some matrix here, and theta 1 dot and theta 2 dot. Here you will have minus 1 as well. Right. So, and this matrix is called the Jacobian matrix. This is the Jacobian of the given kinematic equation. So now we can write this: the position vector velocity x dot is equal to Jacobian of the kinematics multiplied by theta dot vector. Right? So theta dot is the vector of velocities of uh, of the revolute joints multiplied by the Jacobian gives us the velocity of the end effector. But now we see the problem here, that if we want to, you might say that I mentioned that we may want the end effector to move at a certain speed. So then we are given some end effector speed, and we want to find out the speed of the angle, speed of the manipulator angle. Right? So theta 1 derivative and theta 2 derivative, rate of change of theta 1, rate of change of theta 1 are the two variables that we want to find out given the velocity of end effector. For that, we will have to invert this matrix. Then the theta dot is given by J inverse theta x dot. Now, given the velocity of end effector, I can find out the velocity of theta, and then I can actuate the joints using motors such that the desired theta dot, desired velocity is produced at those joints. Okay, but now what is the guarantee that this Jacobian is invertible? So this is a matrix which may not be invertible. It may be invertible. It may not be invertible. What happens if it is not invertible? If it is not invertible, then given the velocity of end effector, we cannot find the velocity for the manipulator joints. Right? So these points are called the singular. Right? So the points where this Jacobian is non-invertible are called singular, and they are called singularity in the manipulator. Side. Are there any messages I need to see? Okay, so there are some internet issues. Okay, right. So now we have covered kinematics, inverse kinematics, workspace, and also the relation of velocities, which is given by the Jacobian matrix, and the inverse Jacobian matrix, which gives us the velocities of manipulator angles given the velocity of end effector. For our case, where do the singularity exist? For this two-link manipulator, singularities exist at theta 2 is equal to 0 or pi. So it is configuration like this. Yes, and then theta 2 is equal to theta 1 and theta 2. Yeah. So here we can see that if this time is theta 1 plus theta 2, cos theta 1 plus theta 2. So if theta 1 is 0, theta 2 is 0, then both the columns of this Jacobian matrix are linearly dependent, and then the Jacobian matrix is singular. Right. So now let us consider this position. So now from this position, uh, the movement is not allowed. So what does the singularity's physical significance is? That is what I'm trying to explain. So now the end effector, this end effector cannot move in x direction. Can it move in x direction? No, because it has reached this limit. Right? So this so if some x dot velocity is given, right, at this location, then there is no theta velocities which can produce that uh, derivative of x, right? So if I say that my x dot is like in this direction, no matter whatever you do with this theta 2 or theta 1, you cannot produce this x dot. Right? So that is what this singular point is. Right? So this is a singular point where you cannot move your manipulator in certain direction. Right? So that is the meaning of this singular point. So wherever singularity occurs, you have a restriction of movement in certain direction. So your end effector can move only in certain direction when your end effector is at singular point. And those singular points are in the workspace, and we may want to manipulate the objects which are located at the singular locations also. So we may need to work around. There is a lot of research available on this topic also. So now the the next item on the agenda will be to design this manipulator in MATLAB using MATLAB's robotic toolbox command, and we want to uh, manipulate this tooling manipulator to make a circle, right? So we want to solve this kinematics and inverse kinematics problem, and then we want to find out the velocities. Yeah, we'll find out this theta dot, which will produce the given x dot and given x, right? So we will find out the manipulator angles which will produce the position of the end manipulator such that this tooling manipulator rotates in a circle. So if a circle is given and I have this tooling manipulator, and then I want my tooling manipulator to trace out this circle. So now I have drawn the wrong kind of circle. This circle is outside the workspace. So the circle may be like I may want to trace out this circle, and I want to I want to solve basically this inverse kinematic problem. So that positions are given. So this circle is in xy plane, is in this xy plane. All the positions are given. All the positions in xy planes are given, and I want to find out theta, the manipulator angles which will produce this position. Okay. So now let us go back to MATLAB and start making this robot. To create a new file and start using the robotic toolbox command now. Okay. So in robotic toolbox command, the first step will be to make this robot. We'll call our robot clear the workspace first. Yeah. So we'll call our robot, and there is a command called rigid body we in MATLAB we can create robots as a rigid body tree. So all these um, links, all these rigid body linked together in the form of tree, right? And then we will say data format is we want to see the data of this rigid bodies as column and maximum bodies that we want to keep right now is three. It's why three bodies because an effector is also considered as a body while making this robot. So an effector is also one of the body and two joints, uh, two rigid bodies, two links are rigid bodies, and the third rigid body is the end effector. Okay. Then we will specify the length L1 is in the previous example we specified L1 0.4 that is 0.4 meter and L2 is equal to 0.3 meter. Okay. Next, now we have created this robot object in this MATLAB workspace. If we execute until this part, we have to save first. Problem that we are going to solve right now. Okay. So, yeah. So if I execute this script right now, you can see here there is a robot rigid body tree object is created in the workspace here with the variable name robot. I can write the command show robot which will open a window to show the robot. But there is no robot right now. We have defined there is nothing defined. It is just empty, just the empty axis which is showing right now. There is no links we have added as yet. Okay. So now let us add some rigid bodies in the robot. The first body is link one. So let the body is equal to a rigid body. We will call it first link one. The joint of this first body we have to specify what kind of joint we are using. We are using revolute joint for this body. So this body right is vertical here. So rigid body joint. Yeah, we will name it joint one, and the type of the joint is revolute joint. Okay. Then there comes uh, transform because when we change these rigid bodies, then the the coordinates have to be transformed in different coordinate frame. For this joint, we have something called this command back to e on 0. We'll see this what this command is doing in a while. First, let us complete the robot, and this command will change uh, for the second joint. So, yeah. So let me put the joint axis then. The next task is to point joint axis. So this joint object is created here. We have created a joint object is a rigid body joint. And this joint object has a property called joint axis. And we have put the joint axis as z axis because our joint, this revolute joint is revolving around That is also an object which has a property called joint, and we will say that this body has this joint. Okay. So now, uh, I hope everyone understands what we have done here. We have created a body which is rigid body. These are all commands in MATLAB in robotics toolbox available. You can write here, let's say, help rigid body, and you get the help of this rigid body command. What it does, it creates a rigid body, the building block of an tree structure robot manipulator. Right? So this is the basic rigid body command given in the MATLAB's robotic toolbox, and we have created a rigid body and named it link one. So the first link from this our tool manipulator, this first link we have created in MATLAB. Uh, now we have created another object called joint. That object is created using the command rigid body joint. We have given the option that this joint is a revolute joint. We name that joint as joint 1, and then transform is fixed. We'll talk about this transform in a while. And then this joint axis is defined, right? That is the z axis. It is revolving about z axis. So these three lines are defining a joint object, and then we have put this joint object into this body. So this body was of the link one, this link one body. So this body has a joint, and we have said that the joint that we have just now defined is inside this body. So that joint is for the robotic link manipulators first link. So the first link has a first revolute joint. Okay, correct. Okay. Now we have defined this body. Okay, and next we have to add this body to our robot. So we have a robot object here which we created at the beginning, and this robot object has to be populated with the bodies, with the various manipulators and various bodies. So, uh, so we will put this body into this robot. So how do we do that? What is the command to do that? The command is called add body. We'll add this body to our robot body, and we'll connect it with the base. Okay, we'll say that this body. Oh, okay. Now, so we have added first body. Now let us execute it and check the progress of our robot. We can check the progress of the robot via command show robot. Okay. So still we are not able to see anything which uh, we will be able to see after we complete this robot. Yeah. So, so this first body is added, then uh, next body will not write the entire code again. We'll just copy paste from code. Yeah. So now we have defined the next body, that is uh, rigid body, uh, link to. Again, we have defined the second revolute joint, and set fixed transform. Here now we have this different vector to transform. Right? So here we have used L1 because we are putting this link to at the location of L1 after the link 1 ends. Right? So that is L1, and then again the joint axis is Z axis. We are revolving around Z axis, and we are adding this robot body We are adding this body to the robot. Okay. Right. Okay. And then the last body that will be added here is the end effector. So the last body is the tool or end effector. We are calling it tool here. This joint is fixed. It is a fixed joint. We are not rotating this end effector, this joint. Okay? So that is this one. This joint here, this joint is not moving. It is not revolute joint. It is not prismatic joint. So that is just fixed joint there. So we have kept it fixed. Then again here a vector to transform it into, and then we are adding that uh, body again to our code. Now we can say that show details of the robot, like we have selected the format of the robot, and we will be able to see all these links, details. So now we can see we have added link 1 with joint 1 type revolute. Parent is base, so it is the first link is at the base, and it has one child called link 2. Okay. So link 1 has a another link called link 2. The link 2 is having joint 2 of revolute nature. Its parent is link 1 and its child is tool, the end effector. And then the tool body is a fixed one, and its parent is joint, and there is nothing further. So there is nothing further in this tree. Okay. Now let us see uh, if we are able to visualize this robot, show this robot. Now, if you can observe the robot is ready. So this two-link manipulator is ready. So we can see here if we go in the XY plane. So this is XY plane. We can see the robot that is started at x00 and x and y00. Its first link of length 0.4 and second link with length 0.3. It's reaching up to 0.7. Okay, so this is uh, the robot, the tooling manipulator is created. You can see the view also of the manipulator. Okay, so we have created rigid link manipulator in MATLAB using MATLAB's robotic toolbox. Uh, I think we can take any questions if participants have here. Are there any questions? I cannot see any in the chat.
No, sir.
Yeah. Okay. Yeah. So then we will move ahead to define the trajectory. The trajectory that we want this to follow is a circle. So we'll define this.
Sir, one question is there. Can you, it's just requesting, can you shift that diagram?
Uh, the shift meaning I just okay. So In which sense I didn't get. This is robot.
So he's asking, can
Where,
you explain set fixed transform command?
yeah, yeah, yeah. That we are going to see. Yeah, that is something we will see. It is very important aspect. Uh, Transform. So this is tr vec. So the command is in this part tr vec to t4. So that is the command. Okay. So let me explain that command first. What is the tr vec to t4? Uh, so we saw this. It is related. The motion is related with this rotation matrix. So, so what is the advantage or why this rotation matrices are used is they give us a linear transformation. Right? So those familiar with vector spaces are aware of the linear transformation or mapping. So this vector um, is mapped to another vector using this linear transformation. So this matrix, this rotation matrix is a transformation. So it is a transform which transforms one vector to another vector. Right? Now, now the thing is, these transforms are very nice. There are very nice properties. Linear algebra is very well understood. That entire MATLAB was built on linear algebra. The Google is built on linear algebra. So linear algebra of transforms is very well understood, and it is nice if we have a transform for everything. If we have a transform which can transform the vectors from one form to another form. But there is an issue when we have the translation motion. So when we add something to the vector, say we have this position x or y, and now we want to move to another position by adding some values to x and y both. And let's say we want to move to a position called x plus h and y plus k. Right? So this is a new position that we want our point to move. But this is not in the transform form. I want a transform. I want a linear transformation because linear transformation, as I mentioned, they are understood very well. There are many algorithms available which can manipulate the linear transformations with nice properties. So we want this operation. Yes, so this operation in the transform form. Right? So this is uh, TR back. TR back is the word from the MATLAB. So this is translation vector. So I'm translating this vector. Okay? I want to translate this XY vector to another vector. So this is vector translation. Okay? And I want the linear transformation. Right? So the transformation which gives me this translation. That is this command which gives us trvec to t form. That is the command in MATLAB which gives us the transformation for this translation. Now, why that appeared in the robot making procedure? Because we want to we want to give the translation motion to our second link by the amount of the length of first link. Okay. So now, if we want to put uh, uh, this translation motion into the form of transform, then how can we write it? We can write it like this. This vector. Right? So actually, we want to go from x y to x k x plus h y plus k, and that transform can be written like this. You cannot do it only with two coordinates. We have to add one coordinate, and this is a homogeneous transformation. So these homogeneous transformations are easy to manipulate. They are uh, easy to understand. So now this xy, which was my original vector, can be translated, can be given translation motion. Earlier, I was giving the rotational motion. Right? So these rotation matrices are the matrices to give rotational motion to my vector. Right? So I have a vector x1, y1, and if I rotate that vector x1, y1, I get another vector x2, y2 via this rotation matrix transformation. Right? So this is a transformation which gives me rotation. But now if I want to translate a point, right? So if the translation is also given as transformation, then that is good from computation point of view. So now if this is the transformation, right, which gives me the translation of this vector. Right? So you can see this matrix multiplication that these two matrices multiplied gives us this vector x plus h, y plus k, and y. Right? So this TR vec to T form command transforms this vector. Right? So if I want to translate it by this amount, right, translate the vector by this amount, it transforms this vector into this linear mapping, linear transformation. I give the TR vec to T form command uh, this vector as input and it will return the matrix, this translation matrix too. Right? We can check this in the MATLAB command window. In the MATLAB command window, let us uh, write this command. Uh, TR vec, so that is translation vector to transformation form, and then our the translation vector is, let's say, the first link we want to translate by 0.4, right? Because the first link takes up the space up to 0.4, and then the second link starts. So when we want to put second link, we have to translate our robot uh, position first to that location. So now if we do this, we will observe the transformation matrix which is 1, 0, then 0.4, then 0, 1, 0, and 0, 0, 1. Okay. So yeah, so this is our transformation matrix where all are identity and only this part is our is the amount by which we have translated our position. Our position has been translated by that amount, right? So you can see here it is something like this 1 0, and then here you have the amount by which we are translating. Okay, so I think that should be clear, right? So yeah, so then that is what we have done here for both the links that fixed transform this joint which we have defined here, it has to be translated by L1 amount, and here it has to be the two the N effector has to be translated by the L2 amount, right? Okay. So now we have created our robot, and now we want to make this robot trace the circle. Uh, I think we will take a break here and we'll meet at 3:15 again to continue this session. Right, madam? Can we
Yes,
take
sir.
a break? Yeah.
Yes, sir.
Yeah.
Participants